What's poppin'? Miss Evans on the beat, so tap in. You got options, but you better pass my class, no flopping. Gon' log in every day, every morning I'm watching. Yeah, we virtual and you know what's up, so we about to take it up a notch. Yeah, Monroe is the best, no comparing. We had to top our truth, no daring. CTAE found arts and sports.
Hey everyone, this is Teach Chem Forever, and today we're going to go over empirical formula calculations. As we have seen, the formula of a compound can tell you a lot of things about a compound. Number one, it could tell you how many atoms are in that particular compound. But what if I had a sample of that compound that I just picked up from somewhere and I wanted to verify its purity? I could do that by calculating the percent composition of all of the atoms in that compound and then testing it against my sample that I picked up from somewhere. For example, if I had NH3 and I wanted to find the percent composition of each atom in this compound, all I would do is basically do part over whole. What is the whole? That's what the entire molecule weighs. So you have one nitrogen, which is 14.01, and you've got 1.008, that's the hydrogens, and you've got 3 of them. So you multiply that times 3. If you add all of that up, you should get 17.034 AMU, or grams per mole. Now, to find the part of nitrogen, all you would do is put the part of nitrogen over the whole compound, which would be 14.01 over 17.034 times 100, because I want to find the percent composition. If you do that, you should get 82.2%. There's only 2 different atoms in this molecule. The other one happens to be hydrogen. So if this is the nitrogen percent, then the hydrogen percent must be 100 minus 82.2, 17.8%. Now you're probably thinking, why am I doing percent composition when this quick tutorial should be going over empirical formula? Well, if I'm given the percent composition, or if I find the percent composition of a compound by its mass, I can determine the empirical formula of that compound. You have seen empirical formula before. We introduced it in chapter 2, and the official definition of an empirical formula, the formula itself shows the simplest whole number ratio of that formula. What do I mean by that? So let's say I have hydrogen peroxide. The formula would be H2O2. If I wanted to get the empirical formula of that just from its molecular formula, I would basically divide all of the atoms by one common multiple. So I can divide everybody here by 2. So if I do that, the empirical formula of hydrogen peroxide would be just HO. Let's try one more. If I have N4H8, if I wanted to find its empirical formula, I can divide both of those numbers by 4. If I do that, it's NH2. So that NH2 is the empirical formula of N4H8. Let me make it clear. If you can't divide all of the atoms by the same number, then you cannot divide at all. So it has to be a multiple of all of the atoms. For many molecules, the empirical and the molecular are the same. They're equal. A good example would be water. You can't divide anything into both of those atoms equally, so that is the empirical formula. Another good example would be methane. We've seen this one before, CH4. That's the simplest whole number ratio. So therefore, that is the same. The molecular and the empirical are the same formulas. And of course, another example would be the one that we did the percent composition for, the ammonia. So now that we understand percent composition and what an empirical formula is, let's go on to do some empirical formula calculations. And here we have an example problem that I want to try with you. Again, the fact that we can determine the empirical formula of a compound if we know its percent composition allows us to be able to identify compounds experimentally in the lab. So if I know the percentage of something, I can relate that to its simplest whole number ratio of the formula, and voila, we've got the empirical formula. So let's try to do that. The problem says a compound is found to contain 50.05% sulfur, 49.95% oxygen by weight. What is the empirical formula for this compound? And then the second part of the question says the molecular weight of the compound is this, 64.07. What's the molecular formula? So given 50.05% sulfur and 49.95% oxygen. So since they equal to 100%, I can theorize that if I had 100 grams of that sample, I would then have 50.05 grams of sulfur, and I would also have 49.95 grams of oxygen. Now, being in grams, we're in a unit that we can work with, that we should feel comfortable with. Once we're in grams, we have to convert these things to moles. Remember, moles are the only thing that you can relate other atoms and other compounds to. You can't do it with grams, you can't do it with particles, you can't do it with any other unit, but you can do it with moles. So let's go ahead and convert both of these to moles. If you look at the periodic table, sulfur weighs 32.07. And if you look at the periodic table for oxygen, it weighs 16 grams in 1 mole of oxygen and 1 mole of sulfur. If I do this calculation, you'll see that you get 1.5606 moles of sulfur. And if you do the calculation for oxygen, you should get 3.1218 moles of oxygen. I want to stop here 1 second to point out that you should not be cutting off your numbers. I will show you why in a little bit, but it's very important when you do calculations for empirical formula, and at this part, when you're finding the moles, do not cut it off. Do not put 3.1 instead of 3.1218. It'll become apparent why you need to do that in the next problem. Once you're here, you have to remember the whole point of the empirical formula is to find the lowest whole number ratio. So for you to do this, you would have to divide by the smallest mole that you have in the compound. My smallest mole is the moles of sulfur. So I divide everybody by 1.5606. That'll give you the empirical formula of this compound. If you do that, you have S is equal to 1. So that tells you that you only have 1 sulfur in this compound. And if you do the division problem for oxygen, you'll see that it equals 2. So the empirical formula of this compound is sulfur dioxide. The second part is, given that the compound weighs 64.07 grams per mole, what is the molecular formula? To do this, you first have to figure out what this empirical formula weighs. Sulfur weighs 32, and you've got 2 oxygens, so therefore 32 plus 32 is 64. That means that the empirical formula, which we found, is the same as the molecular formula, because the empirical formula only fits once into the molecular formula. If we do another problem, it's the same setup, except we're going to use different percentages and different atoms. Let's say a compound is found to have 57.54% of carbon. You've got 3.45% of hydrogen and 39.01% of fluorine. I want to know what the empirical formula of this compound is. I would also like to know what the molecular formula is, given that its molecular formula weighs 438 grams per mole. The first thing I need to do is, I can't really work in percentages, so we're going to convert everybody to grams. The first step of this problem is to convert everybody to moles. Okay, if I do all these calculations, you should get 4.791 moles of carbon. You should get 3.423 moles of hydrogen. You should get 2.053 moles of fluorine. At this point, you need to divide by the smallest number you have. If you look, the smallest moles is this one. It's 2.053. So if you divide everybody by 2.053, you will get, for carbon, you're going to get 2.333. For hydrogen, you're going to get 1.67. And of course, for fluorine, you're going to get 1. But this is something different. This is a problem because we cannot have, this tells you that you have 2.333 moles of carbon. You can't have a fraction of a mole. So we need to fix this. Remember, the definition of the empirical formula is whole number ratio. So these are not whole numbers. So therefore, you need to be able to multiply everybody by the same value to make it into a whole number integer. So if you think about it, if you multiply this times 3, this times 3, and this times 3, carbon is equal to 7. Hydrogen, 1.67 times 3, is equal to 5. And of course, 1 times 3 for the fluorine is equal to 3. So the empirical formula of this compound is C7H5F3. Remember I mentioned not to cut off your numbers? If, for example, in this step, you just did 4 moles of carbon, 3 moles of hydrogen, this answer that you would get here would not be exactly 2.333. You would then have the opportunity to not be able to multiply at the end by a whole number integer, by a digit that will get you to a whole number integer. A question may come up that you ask, well, how do I know when to multiply times something? It will be very clear. For example, you will either get something extremely close to the whole number, like if you get 4.99999, that is a 5. But if you get a third, or if you get 2/3, something sort of in the middle, or if you get a half, carbon 2.5, you can't just go ahead and say, well, I'm going to go ahead and say that's 2 carbons, or say, oh, no, I'm going to go ahead and say that's 3 carbons. You can't do that because that's way off from being super close to a 2 or a 3. The second part of this problem asked if I had this empirical formula and given, remember up here, we had 438, given that the molecular formula weighs 438 grams per mole, what is the molecular formula? The first step to do this is figuring out how much this empirical formula weighs. When you do that, you should get more or less around 146 grams per mole. From here, you have to figure out, well, how many times does this amount fit into this amount? So basically just divide 438 divided by 146 should give you 3 times. So that means that you have to multiply the empirical formula 3 times to get the molecular formula. Then the molecular formula will be 7 times 3, that'll be C21, 5 times 3, that's H15, and 3 times 3 is F9. So that is what the molecular formula is, which weighs 438 grams per mole. Thank you so much for joining me, and I would like to remind you to please read these sections in the book. I want you to please look at these videos, and of course think about these questions as you're going through these problems. It'll help you better understand the concept. All right guys, I'll talk to you later.